Hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on aside as we begin Chapter 2 in the Big Ideas Math Integrated Math 1 textbook. This chapter is completely on solving inequalities. Now, in the last chapter we were solving linear equations. Equations means equal sign. Inequality to you will mean less than, greater than, less than or equal to, greater than or equal to, that kind of scenario. We've probably seen them before, but now we're going to be doing them with representations on variables, graphing them, writing them, solving them, all that stuff. Now, section 2.1 is what we're on right now. This is writing and graphing inequalities. This does not involve solving. In fact, the solving doesn't start until the next section, and we're going to slowly go through those ones. So what you learned on Chapter 1 in solving equations will start taking hold in the next section at a very basic level, just adding and subtracting, and then we'll multiply and divide, and then we'll do multi-step. We'll do it very slowly, which is nice. They're shorter sections, which is also nice for me personally, but the shorter sections, you ease into them, but what you want to know in section 2.1 is going to lead you into it. So you can learn 2.1 without knowing anything from chapter 1. If you still need time to slow down on chapter 1, go ahead and do that. But we're going to learn the graphing and writing of these. If you want to follow along, you can download this PDF down below in the description section. You can also find timestamps to the problem set as I begin the lecture portion. Find my IM1 playlist down below as well if you're trying to find any other corresponding videos. Without further ado, I'm going to go ahead and get started with the lecture portion. Okay, we are going to write inequalities, linear inequalities. Everything's linear. Sketch the graphs of linear inequalities and write linear inequalities from graphs. Awesome. Now again, inequalities are these symbols right here. We can see them. What we are first going to begin with is representing inequalities. Remember, we don't say equations anymore. We're going to say inequalities. Representing inequalities from words, translating them to inequalities. So we have to know some phrasing of them. When you see this guy right here, this means is less than, or in another way, is fewer than. There are probably some other kinds of wordings that you can say in the English language, depending on context, is cheaper than, is shorter than, is lower than, right? There are different things that you can do to compare. Now, keep in mind, when we say is less than, you've probably heard somebody say like, hey, think of this like an alligator mouth, Pac-Man, whatever, and it wants to eat something that is bigger. It wants to eat the 4 when this is a 1, right? That kind of thing. Eats the bigger number. Yeah, yum, yum, yum. Keep in mind, when we say is less than, that's comparing the left number to the right number. 1 is less than 4. But hey guys, 4 is greater than 1. So whenever we see this symbol, you have to remember it's read in a left to right manner. Don't forget that. The is greater than is this way, right? If I compare something like 5 and negative 2. 5 is greater than negative 2. But negative 2 is also less than 5. So when read left to right, we're seeing this as a greater than symbol. Keep that in mind. These symbols are less than or equal to, greater than or equal to. Keep in mind, you cannot be both less than something and equal to something at the same time. So the word is or in between. As long as you satisfy one of those two conditions, then we're good, right? When we say 3 is less than or equal to 4, that's a correct statement. It's not equal to 4, but it's less than. If it said 3 is less than or equal to 3, 3 is not less than 3, but it is equal to 3. So it's still a correct statement. So keep in mind on the less than or equal to, that's what that means. And same with the greater than or equal to as well, obviously for greater than standards. So we're going to start by writing inequalities, writing sentences as them. They're going to be pretty literal with these. And I want to let you know that in sections, I think it was 1.2 and 1.3 or something like that. They were in the problem sets, not in the lecture portion. They didn't do a breakdown of these, but they had questions like these. And so when I was doing them, I said, I guess there's some level of understanding that you've done this before in the Big Ideas Math curriculum. So you probably have done translation into sentences for equations, but not for inequalities. Now, these ones look pretty direct, pretty literal. A number w minus 3.5 is less than or equal to negative 2. It looks like they're telling you exactly what to write in that scenario. But what I wanted to state before was when I said the word is separated the left expression from the right expression, this expression now has a little bit more, the is now has a little bit more phrasing to it. Now it says is less than or equal to. So this phrasing separates the left expression from the right expression. Now we have to see a little bit more with that word is in order to make sense of what's happening there. Because there's a difference between saying number like w whatever minus 3.5 is less than or equal to negative 2 versus is 2 less than a number. right? 2 less than a number, subtracting 2 from a number, but the is just an equals. But is less than is a part of that whole phrasing. So they break this down perfectly in color, and I want you to just be able to see these examples for what they are. A number w minus 3.5 is less than or equal to negative 2. So that's the way that we'll write that inequality. We're not solving these ones, by the way. We're just writing them, at least to start with. 3 is less than a number n plus 5. Boom. And keep in mind, this is written left to right to accommodate the less than. Now, could I write it this way? Yes. Would that be tricky for the reader to look at? Absolutely. But this is still a correct version of that. A number n plus 5 is greater than 3 is, kind of the other version that you can say. It's still the same thing, and I'm just mentioning that because there are times where I'm going to be flipping around an inequality. I like my variable on the left side of these ones. Despite what I said about equations, when something doesn't matter, I really want my variable on the left side of these ones, ultimately. 0 is greater than or equal to twice a number plus 1. And there you have that one as well. So like I said, these ones are pretty literal. I'm expecting to get more ones, like the sum of 3 and a number is no more than, that half that number. Things like that can probably get a little tricky. We'll see if they do something like that. Okay, let's move forward. A solution of an inequality is a value that makes the inequality true. An inequality can have more than one solution. An inequality will probably have an infinite number of solutions. When I say something like x is greater than 7, I'm thinking of every number in the world that's greater than 7. Not just 8, 9, and 10, but also 100 and 1,000 and a billion, and also even, 7? 7.1 is greater than 7. 7.01 is greater than 7. You have an infinite number of values that are greater than it. So keep in mind, that's going to be true. They're doing a test here for x plus 5 greater than or equal to negative 2. They try negative 6, negative 7, negative 8. Negative 6 plus 5 is negative 1. That's greater than negative 2. It's not equal to it, but it's greater than it, so it satisfies it. Remember, smaller negatives are actually larger values because they're closer to 0. They're closer to positive territory. Negative 7 plus 5 is negative 2. It may not be greater than negative 2, but it is equal to it, so that also satisfies the inequality. Negative 7 is good. And then negative 8 doesn't because you have negative 3. Negative 3 is not greater than negative 2. It's not equal to negative 2. It's actually less than. Larger negative numbers are smaller. So you start to see the threshold between what does and doesn't work in the scenario just by testing points, unless they request certain points. So let's check some solutions here. Let's tell whether negative 4 is a solution of each inequality. We're going to substitute negative 4 for x on part A and on part B. On part A, negative 4 goes in x's place. Negative 4 plus 8 is 4. Is 4 less than negative 3? No. In fact, no positive number is less than a negative number, or 0. That would be impossible. Let's try and substitute negative 4 into here, which again, use your parentheses, substitution. Negative times negative is a positive. I don't care what the number is. If it's positive, it's going to be greater than that negative number. So 18 greater than negative 21. Therefore, negative 4 is a solution to this inequality. Was not a solution here, was a solution there. Now, as far as solutions goes, we can also graph their representations. The graph of an inequality shows the solution set on a number line. See, for equation number lines, that doesn't really mean much to us. To say x equals 7 doesn't mean very much for us to put a 7 right there and just draw a dot, right? But inequalities are a representation of every number that exists for that set. It's not just one number. It's everything that's greater than this, everything that's less than this. Maybe that's equal to it. Now, they mention an open circle versus a closed circle. An open circle is something where you don't fill it in, and a closed circle is one that you do. Now, we tend to do these on what I call, and what is generally called, a boundary point. And I say that because I don't believe the book is using that phrasing. It wasn't in the glossary set. I don't see it on this page. But this is what's considered your boundary point. By the way, don't mistake that for an open circle. I'm just showing. This is what I would call a boundary point. A boundary point is the threshold. It's the point, the value that separates your solutions from things that are not your solutions. Now, the boundary point may be a solution. In this case, it is. We'll see the example in a second. And here's another boundary point that's not a solution, right? I'll just call it BP. It's not a solution. But that's where we draw the open or the closed circle. Why would we do it? Because a closed circle is a solution. Where is it? A closed circle is a solution. And in the case of part A, example A, y is less than or equal to negative 3. Here are all the y values that are less than or equal to negative 3. Negative 3 is equal to negative 3, so we put a closed circle on negative 3 to represent that boundary point. What are numbers that are less than it? Well, they say test a number. I'm likely not going to do tests of a number, and I'm going to graph based off directionality. If my variable is less than my number, we'll look at numbers as far as a test. Negative 4 works. Negative 4 does work. It's less than negative 3, and it's to the left of it. Less than is left is the way I like to say it. And they test 0 as well. 0 is not less than or equal to negative 3, so 0 is not a part of the solution set, so we don't graph on that side. Anything on that side of negative 3 will work to the left of it. We'll go that way. Now, I'll let you know that I'm not going to be as detailed in my graphs. I'm only really going to just graph the following. I'm going to draw my number line. I'm going to give you 0 and my boundary point, my boundary value. I'm going to draw a boundary point on my boundary value, and I'm going to graph in the direction that I go with including that variable like so. By the way, that's an arrow that I'm doing right there. So that's the extent to which I'll do this stuff. I will test 0. I'm fine with that. 0 is very easy to compare to because 0, like I said, is always greater than negative numbers and always smaller than positive numbers. I won't test 0 if 0 is the boundary point. I can test other numbers, positive or negative, that way. Now, part B is a little bit different. For one, it shows a less than and not less than or equal to. That means when it comes to boundary point, it is going to be an open circle to indicate that 2 does not work. Neither does anything on the side of 2 that doesn't work. But anything on that other side will work, just not 2 itself. 2.01 is fine, things like that. But this says 2 is less than x. Now, I just said that less than is left. So when you saw this one, you're thinking, hey, less than, we're going to go to the left. And we did. But why? How come when 2 is less than x, they went to the right? Is this a mistake? No. See, if you test 0 in here, is 2 less than 0? No. So 0 shouldn't be a part of your solution set, so we should go to the right. But Mr. Robinson, if you said less than is left, how will I know which direction to go? It looks like I should test points. Well, you probably should test points. I don't mind you testing especially 0 each time. Really easy comparison. But remember, this says 2 is less than x. What if you turn everything around? What if this said x is greater than 2? I mean, literally, this thing can turn around. If 2 is less than x, that also means x is greater than 2, right? There's a turnaround there. Compare your variable to your number. Put your variable on the left side of the inequality, and that's where you'll get true statements. This is greater than. This is to the right. Our numbers are greater than our boundary value. That's where we go to the right. These are our x values. Now, how would I draw that graph? I will be going number line, 0, 2, open circle, to the right, place my variable like so. Again, I'm fine testing 0. Like I said, I'm just not going to test a bunch of points left and right. I'll test 0 in that situation. The third example is x is greater than 0. Okay, this time 0 sounds like it's our boundary point. Now, before I reveal the answer, we might have already seen it, I don't know. But before I reveal the answer, think about what you're going to do. 0 is the boundary point. Because it's greater than, variable greater than, we're going to graph to the right. It can't include 0, so we'll put an open circle on it. So open circle on 0, graph to the right like so. My graph in particular will just have 0, an open circle, and that direction. Now, what kind of numbers can I test? Positive numbers or negative. You can test any number that's not 0 this time, right? Is 2 greater than 0? Yes. Well, 2 is on this side of 0 to the right. Is negative 4 greater than 0? No. Negative 4 is on that side. I don't graph that. So we only graph solutions, and this arrow, this marking, represents everything that's a solution. Okay, writing linear inequalities from graphs. The graphs show the height restrictions h in inches for 2 rides at an amusement park. Write an inequality that represents the height restriction of each ride. So there's ride A. I can't tell. Wait. Okay, so I thought these were the answers. So this ride here shows you that you can be, this is in inches, you can be 48 inches tall or 49 inches or 50 inches or whatever in between there or taller than. Ride A is 48 inches or taller to ride. That's 4 feet or taller. Ride B shows 52-inch mark. If you're at 52 inches, you're too tall. It's not allowed, but you can be shorter than 52 inches here to ride. Maybe just the way that the restraints are, the weight and stuff like that, obviously, like kiddie rides, right? Whereas big boy rides on these ones. The closed circle means 48 is a solution because all numbers greater than 48. So h is greater than 48 represents the height restriction for ride A, and h is less than 52 represents the height restriction for IB. I'm sorry, I thought that they were saying, I'm fine writing the inequalities. I thought they wanted us to use actual context and say 48 inches or taller is good. But okay, h is greater than or equal to 48 inches. H is less than 52 is less than 52 inches. Okay. Representing linear inequalities as a concept summary, once again, compare x to 2, greater than, less than, or less than, greater than, less than or equal to, greater than or equal to. Less than is left, boom, boom. Greater than is right, boom, boom. Equal to's are closed circles, not also equal to are open circles. Okay, that is the end of the lecture portion. Let's start with the vocabulary and core concept check. We are going to problem 59 as a whole. We have questions 1 through 4 to begin with here. A mathematical sentence using these symbols is called an inequality. And keep in mind, guys, these are not equations. You can have the or equal to portion, but it's not exclusively equal to. It's also possibly less than or greater than. So inequality you're thinking of not necessarily equal to, how it compares to it in that way, or contrasts from it. Number 2, vocabulary. Is 5 in the solution set of x plus 3 is greater than 8? Explain. Well, 5 plus 3 is 8, and 8 is not greater than 8. No, because 8 is not greater than 8. So the bottom line is you're doing a substitution of 5 into x. Number 3, attending to precision. Describe how to graph an inequality. Well, I just stated it on the previous one, and I don't really have much room to do here. Let's go and rotate this one up. I like to just, I don't know how many people do these. Like, I don't assign these kinds of problems to my students often, really, almost ever. So I don't know if these are ones that people listen to unless you just want to get vocabulary core concept check. But here's where I'm going to fit it. First of all, for me personally, I compare the variable to the number. Compare the variable to the number, meaning variable on the left, number on the right. Less than is left, greater than is right. Okay, that's the start. Less than is left, greater than is right. Equal to equals closed circle, meaning including it. Not equal to equals open circle, which means excluding it. You graph in the direction of the boundary value. I know that that's not a lot that I was saying there. The number is the number, I'm going to say the boundary value. The boundary value. Okay. Hopefully that makes sense, and it'll make sense, obviously, when we do the graphs. Number 4, different words, same question. Which is different? Write both inequalities. Okay, here we go. W is greater than or equal to -7 looks like this. W is no less than -7. It's no less than it. No less than. You can have no less than. Let's see, people don't normally restrict you that way. You must have no less than 5 pieces of broccoli, right? No less than, but you can have that many, 5, or you can have more. So in this case, -7, W is greater than or equal to -7 also works there as well. No less than. W is no more than -7. You may have no more than 5 pieces of chocolate. Oh man, no more than 5 friends over. You can't have more than. No more than. You can have less than. You can have that number. This is less than or equal to -7 or equal to. So that's different. This is the different one. I'm sorry. This is the same. W is at least -7, at least that or more. This and then some. -7 is the absolute least. If you have it smaller, that'd be a problem. So that's also greater than or equal to -7 there. So there's the wording, and that's good to kind of jump into those that way. Okay, let's go ahead and start with problem numbers 5 to 59. These might go pretty breezy. I'm not sure. Depends on how many things I have to kind of teach as we do them. But let's go ahead and get started. Okay. Numbers 5 through 12 write the sentence as an inequality. Now, I am not going to rewrite the sentence, but I might do some breakdown on this side of the problem here. Now, remember, I'm looking for the word is to separate this parts of the inequality. It's not just is, though. In this case, it's is greater than. And that's what separates the left expression from the right expression. It says a number x is greater than 3. That is as literal as it gets. X is greater than 3. It looks like that. Number 6, in fact, a lot of these look like they are pretty literal. We'll see what happens from there. But a number n plus 7, that sounds like an expression, is less than or equal to, boom, there's the inequality, 9. A number n, and this is read left to right, so a number n plus 7 is on the left, is less than or equal to, is there, and 9 is the right expression. Number 7, 15 is no more than, so is no more than is our phrasing this time, a number t divided by 5. So here's 15, here's the number t divided by 5. They didn't say is more than, they said is no more than. So it can be it, and it can be less than it, but it can be no more than it, a number t divided by 5. And notice how I put this as a fraction. I'm not really using the division symbol in that case, right? It's too archaic for us. Number 8. 3 times a number w is less than 18. Again, that's pretty literal there. That is less than is our phrasing for our inequality, literally for less than. So 3 times a number w is less than 18. Keep in mind, we are not solving these. We're just writing them. So that when we do solve them, we'll be so ready and graph them. Number 9, 1/2 of a number y is more than 22. More than is also a way of saying greater than. Why did that turn black? Is more than 22. Okay, so like greater than, right? So 1/2 of a number. That means 1/2 times a number. 1/2 of a number y is more than 22. Number 10, 3 is less than the sum of a number s and 4. It's not 3 less than the sum of a number and 4. It's not an expression. Literally, though, if you took out the word is, it's a completely different statement. So I'm gonna kind of show you what both look like. But 3 is less than, here's 3. 3 is less than the sum of a number s and 4. That's the sum of these two added together. Now, what if it said 3 less than the sum of a number s and 4? That would take the sum of a number s and 4 and take 3 less than that. That's a completely different thing. For one, it's a subtraction. For another, it's not even an inequality or an equation. It's just an expression now. And another, 4 minus 3 is 1. But yeah, two-way different things just because the word is there. But is not the entire phrasing of the symbol. 13 is at least the difference of a number v and 1 is at least meaning that or more. So 13 is at least, not less than, at least the difference of a number v and 1. And number 12, the thing about these ones though is that I'm almost doing that thing where I'm just repeating the phrase over and over and seeing if it, you're like, Mr. Robinson, just because you're saying the phrase over and over doesn't make it easier for you. You keep saying is at least. That's not helping me. The reason I'm saying that is because I want you to think in terms of sentences when you've said that, right? This video is going to be at least 3 hours long. Oh my gosh. That's right. That means if I said at most 3 hours long, you go, oh, okay. Like no more than 3 hours, right? Anyway, so I'm just making sure you kind of get that. I want you to use other sentences, English. 4 is no less than the quotient of a number x and 2.1. Okay, let's start with the 4. The quotient is division. X and 2.1 are being divided like that. Boom, boom. Now, what's in between here? Again, this video will be no less than 3 hours. Oh my gosh, that means it won't be less than 3 hours. It means it'll be 3 hours or more. So 4 is no less than x over 2.1. By the way, I don't anticipate that for this video. No. I'm just kind of giving you the idea of, oh, if I think about it that way, maybe that'll help me. Okay, anyway. Okay, number 13, modeling with mathematics. On a fishing trip, you catch 2 fish. The weight of the first fish is shown. It's right here. It says 1.2 pounds. There's the weight of the first fish. Poor little guy. The second fish weighs at least 0.5 pounds more than the first fish. At least 0.5 pounds more. Okay. There I go again with it. Write an inequality that represents the possible weights of the second fish. We're not writing different numbers like, oh, it could be 5 pounds, it could be 6 pounds. Not like that. We're writing out the whole inequality. They didn't give us a variable here. I'm just going to put x for the weight. The second fish weighs at least 0.5 pounds more. So x, this weight, is at least greater than or equal to whatever the fish's weight is, plus an additional 0.5 pounds. Okay, 0.5 more than. The more than there is not part of the inequality statement. The more than is increasing this number here. So it's at least half a pound bigger. That means it's at least 1.7 pounds. That's what we're stating as a statement there. Okay. Number 14. There are 430 people in a wave pool. Hi. Write an inequality that represents how many more people can enter the pool. So there's a maximum capacity of 600. So how many more people can enter the pool? Remember, this doesn't mean exactly this many need to enter the pool, that, hey, we need this many more people, like that kind of thing, right? But what we need to figure out is the difference between the maximum capacity and the number that we have, okay? The number of people who can enter the pool is at most the difference between the maximum capacity and the number of people currently in the pool. So it's the difference. At most, this is how many we can have. So we can have this number or less. 600 minus 430 is 170 people. At most, this many more people can come in. That doesn't mean you have to have exactly 170 though. That's why I like inequalities, because these are reasonable for these kind of scenarios. We don't have to be exactly equal a lot of times. We just need to kind of be within that amount or outside of that amount, which is pretty cool. It depends on the situation. Sometimes you have to be equal. Numbers 15 to 24 tell whether the value is a solution of the inequality. So I'm going to copy the problem down. We have r plus 4 is greater than 8, and we're going to test r equals 2. So we're going to substitute 2 for r. Is 2 plus 4 greater than 8? Oops. 2 plus 4 is 6. 6 greater than 8 is a no-go. So no. I'm going to put yes in green, no in red. Is 2 a solution? 2 is not a solution because it did not satisfy the inequality when substituting. Number 16. We have 5 minus x is less than 8. And keep in mind, we're not solving the inequality. We are testing a solution, a possible solution to the inequality. So now I substitute negative 3. By substitution, you want to use parentheses outside it with this negative. So this is 5 minus negative 3 or 5 plus 3. And 5 plus 3 is 8. As 8 was not greater than 8, it too is not less than 8. This is also not a solution to the inequality. Number 17. 3s is less than or equal to 19. And s equals negative 6. Let's substitute that. That's 3 times negative 6. Automatically, I'm seeing a positive times a negative. That will be negative. And at this point, it doesn't matter what the number is. If a negative is here and a positive is here, a negative will be less than a positive or equal to it. Actually, not equal to it, but less than. So as long as it satisfies one of them, the less than, it's all good. This is a yes, ding, ding. Number 18. Now this time the variable is on the right side of the inequality. I said I like writing it on the left side, but since we're doing a substitution, I couldn't care less here. I'm just trying to see if 17 is greater than or equal to the number that we end up having. In this case, for y equals 7, we're going to be checking 17 compared to 2 times 7, or 17 compared to 14. Is 17 greater than 14? Yes. Is it equal to? No. Does that matter? No. It just needs to be one or the other. 17 is greater than or equal to 14. We are good. Number 19. Now we're going to do division. And we have a negative fraction on that side. And on the other side, the left side, we also have a negative number. So it's a direct comparison of two negatives as we substitute this positive number, 3. We have to compare negative 1 to negative 3 over 2. So this gets tricky for a couple things. First of all, you have to know how negative 3 over 2 just is represented as a decimal, maybe. Maybe we can write it as its decimal, negative 1.5. So this might help. Now, is negative 1 bigger than negative 1.5 or less than? Keep in mind, they're negative numbers. What I stated before and what we have to keep in mind, especially when we start doing number lines, is that on this number line, like here's 0, negative 1, negative 2, etc. On a number line, numbers to the right are bigger than numbers to the left. Well, here's negative 1, and here's negative 1.5. Negative 1.5 and negative 1. Negative 1 is greater than negative 1.5. That's a true statement here. This is a yes. Smaller negatives are larger in value because they're closer to 0 or closer to positive. They're further to the right on the number line. So that's how that would compare. So it gets a little trickier on that problem, but we want to make sure that we avoid any mistakes there. Number 20, 4 over z is greater than or equal to 3, where z equals 2. If you're not careful, you're just going to write z as 2's anyway. So 4 over 2 is greater than or equal to 3. Let's see. Is that true? Is 2 greater than or equal to 3? It's not greater than. It's not equal to. That's a no. Welcome back to the no's. Number 21. 14 greater than or equal to negative 2n plus 4. Our n is negative 5. So our substitution will include parentheses, given not only the negative, but the multiplication. Negative 2 times negative 5 plus 4. Negative 2 times negative 5 is positive 10, and 10 plus 4 is 14. Is 14 greater than 14? No. But is it equal to it? Yes. So number 21 is a yes, that negative 5 is a solution to this inequality. Among another infinite set, not all real numbers. I want to remind you that inequalities have infinitely many solutions. That doesn't mean it's all real numbers. Number 22 says negative 5 divided by 2s, as in 2s is a quantity that goes in the denominator, and I'm probably going to rewrite that as a fraction. This is compared to negative 1 as if to see if it's less than it. Well, it is less than it, but when I substitute 10, is it still less than it? Let's try negative 5 over 2 times 10. Let's write it like that and compare that to negative 1. So both negative numbers ultimately, right? This is negative 5 over 20 and negative 1. Now, whether or not you know what this fraction is as a whole, which, I feel like you should when you reduce the fraction stuff, it's a smaller number divided by a bigger number. That means the number itself is less than 1. I'm not talking about negatives. I just mean 5 over 20. 5 over 20 itself is a number less than 1. Now, how does a smaller negative number compare to a larger negative number, right? Anyway, that's negative 1/4 or negative 0.25. Negative 0.25. So, how does a smaller negative number compare to a larger negative number? This should be bigger than that, but they say less than. So that's not true here. This is a no for number 22. If you need to go back to the number line for that, you can. Absolutely. Number 23. I don't know if these are necessarily getting more difficult. They're jumping around different cases here, so I don't know if they're trying anything trickier on these next two. 10 over 2z plus 20. Okay, there's a plus 20. Z equals 5. So we're going to check 20. Is it less than 10 over 2 times 5 plus 20? So this is 10 over 10 plus 20. Now, we got so used to saying these cancel out. Guys, they don't cancel out. 10 over 10 is 1, right? They divide to become 1. Sorry, I shouldn't say I got comfortable with that because I didn't. That is what it is. But 20 is less than or equal to 21. That sounds true, right? So that's a yes. Now, I'm doing all the steps on top of them just to kind of cover my bases. In the future, maybe not so much. But I did also mention, this is why I like testing the number 0. The number 0 does several great things for us. 0, and I'm going to say this more than once. 0 times anything is just 0, and 0 plus anything is just that thing. So it's a lot easier to do calculations. You get to wipe things out significantly faster when you test a 0. See, if this said m equals 0 instead of m equals 8, well, this wipes out and it becomes negative 2, right? That's a lot easier. But m equals 8, we got to do a calculation. So let's try it. 3 times 8 over 6 minus 2. 3 times 8 is 24. 24 divided by 6 is 4. 4 minus 2. And don't stop till the end. I know even if you know this answer, then write it. 2 greater than 3, not so. So no. Right? We do the same thing with equations on double checking. We go until the left side and the right side are down, simplified down to just a single value. But that's a no. Excuse me. Okay, number 25. The tallest person who ever lived was approximately 8 feet 11 inches tall. We want to write an inequality that represents the heights of every other person who has ever lived. So with this one here, and I don't think we're doing compound inequalities yet, but one of the things I'd state is you can't be negative people, so greater than 0 is a part of it. I'm going to leave that out for now. We're just going to talk about the heights, assuming they're positive numbers, and I'm going to put an H for height. Every other person who ever looked, they said the tallest person, the one tallest person. So no one else has met this height. They've all been less than it. So what do they say? Well, here's the other thing. 8 feet and 11 inches is not easy to write as a number. We don't say H is less than 8 feet 11 inches. We have to convert this either to feet with a decimal. That's not 8.11, by the way. And it's a weird decimal. I'd rather convert it to inches. So 8 feet and 11 inches equals 8 feet times 12 inches per foot plus the 11 inches, which is 96 plus 11, which is 107 inches. So as far as people's heights, no one has met 107 inches or exceeded it. Every other person's height in the world has been less than 107 inches as a whole. That's how I'm going to be writing that. Part B is 9 feet a solution to the inequality. Explain. Well, 9 feet is more than 8 feet 11 inches, but even if you get to, let's see, I'm going to put this part A. Actually, this is part A here. Part B, I'm going to say 9 feet. I'm going to compare as this number here. 9 feet is 9 times 12 inches, which is 108 inches. So, is 108 less than 107? No, as 9 feet is not less than 8 foot 11. No. Explain. I'm showing the inequality as my explanation. See, you can explain through math in some ways, and that's what I did there. Okay, drawing conclusions, number 26. The winner of a weightlifting competition bench pressed 400 pounds. The other competitors all bench pressed at least 23 pounds less. So, what is 23 pounds less than 400? This is what every other competitor did. Write an inequality, part A, that represents the weights that the other competitors bench pressed. I'll just put X for competitors here. They all bench pressed at least this many less. Oh, geez. Hold on a second. So when it says less there, we did that. But at least in this case doesn't mean they did that many or more. So let me do a slight revision on this. The amount that they bench pressed was at least this much less than that. So this is one way to write it to begin with. Now 400 minus 23 is 377, but I'd prefer to write it now in this direction. If 377 was the most that we did compared to X, then X had to be that or less, right? So just kind of different versions of how we're coming up with that. By the way, this is in pounds. Let's do a little LB there, LBS. Okay, part B. Was one of the other competitors able to bench press 379 pounds? Explain. No, 379 is less than or equal to 377 is not true. So that would also be a no. It's not a solution to the inequality. Okay, numbers 27 and 28 describe and correct the error in determining whether 8 is in the solution set of the inequality. So on both problems, they are going to substitute 8. So on number 27, let's take a look at what they did. Let's take a look at where they went wrong. Negative y plus 7, that's the original. They did a substitution, that's fine. Negative 8 plus 7 is negative 1, that's fine. Negative 1 less than negative 4 was their statement. By the way, they put a question mark, which is a good thing to do. Is it less than? Is it? I should be doing that. That's just a lot more work for me to write, and ultimately I go in my final conclusion. Their final conclusion was that negative 1 is less than negative 4. That's not the case. It is not less than negative 4. So they said 8's in the solution set because of their conclusion, because of what they decided. Their math is correct, but negative 1 is not less than negative 4 for a couple reasons. It's a smaller negative number because it is closer to 0 and positive numbers. So therefore, the final statement should be negative 1 is not less than negative 4. Therefore, 8 is not in the solution set. Now, normally I don't write the answer like that as a whole, but in this case I am, just to kind of make the correction there. So boom. Number 28. They substitute 8 for x. Half of 8 is 4. 4 plus 2 is 6. They said 6 is less than or equal to 6. Well, this time they didn't cross it out. Normally we do the cross out thing because they said not in the solution set. So I expected a cross out here. But they said 8's not in the solution set basically because they would have crossed this out. They said, oh, this isn't a true statement. They're like, 6 isn't less than 6. But here's the thing. It's less than or equal to. In their final statement of 6 is less than or equal to 6. I'm coming up with the less than or equal to symbol. Give me 1 second. Of 6 is less than or equal to 6. They apparently declared the statement false because they said 8 is not in the solution set. However, and I don't have to type this much. However, 6 equals 6, so that statement is true. Therefore, 8 is in the solution set. And that's my correction. So remember, less than or equal to 6. 6 may not be less than 6, but it is equal to, and that's part of the statement for this scenario. All right, in exercises 29 to 36, we are to graph the inequality. Graph the inequality. Now, they are going to be big on, like I said, testing numbers. The most I'll test is the number 0, and I'm pretty much going to do it after the fact. Number 29 says x is greater than or equal to 2. What I also stated on these things here is I'm going to graph the number lines pretty basic. I'm going to place 0 on here and my boundary value. My boundary value is 2. I'm going to place a boundary point on there. Because x can also be equal to 2, 2 is a part of it, I'm going to draw a closed circle on there. When x is greater than 2, what are numbers that are greater than 2? 3, 4, 5, 6, 7, 8, numbers to the right of it. Greater than is to the right, therefore my x's can be 2 or numbers to the right of it. That's an arrow, by the way. I can test 0. Is 0 greater than 2? No. Therefore, it's not part of my solution set. Number 30. Z is less than or equal to 5. Z number. On this number line, here's 0 and here's 5. Z is 5 or less. So 5 counts. Anything less counts. Less than is left. We're going to go this direction for Z. This should include 0. Let's test it and see if it works. Is 0 less than or equal to 5? Yeah, 0 is less than 5, so that works out. Anything greater than would not. Number 31 says -1 is greater than t. Now, the thing to be careful of is how this greater than is going to fit with this because the way that this is written. So take a look. First, I'm going to start with boundary value of -1, which is to the left of 0. Now, as far as the greater than symbol goes, equal to is not on there. Therefore, there's an open circle. But do I graph to the right or to the left? You see greater than, you think to the right. But let's test. I'm going to draw this in red to begin with to say let's test 0. If I test 0, I should get a true statement. Is -1 greater than 0? No. I should be graphing to the left instead. Now, how come this greater than says, how come it says greater than if we go to the left? Because the variable is on the right side of the equation. If I flip everything over, this would say t is less than -1. The mouth, the alligator mouth, whatever you call it, still eats the bigger number. It's still eating -1, and I'm flipping it over that way to represent it best. You're going to see me do this for every problem here on out, at least that I can and talk about. I might remind you on some of them in future sections, but writing the variable on the left side is going to be the best thing for you to do to not make that mistake, especially when we see that word less than. Yes, you can test points. Yes, you should test points. I keep testing 0, but you can see on this problem again, I'm going to do the same thing. Rewrite this. W is greater than -2 is the way I want to compare it. Greater than now means to the right because I get to compare my numbers to -2 this time. So W is everything greater than -2. It doesn't include -2. It's not equal to it. 0 is included. Is 0 greater than -2? Yes, it is. Or is -2 less than 0? Yes, it is. Maybe you should compare to the original inequality, but that's what works out. Number 33, v is less than or equal to -4. Variables on the left side, which is good. Now, again, the reason I put 0 on here is so we can do a fair comparison of it to there. 0 is a very easy number to compare to, especially positives and negatives. Less than is left. We're going with v, every which direction there. You do have to draw the arrow. Whether I'm closing the arrow or not doesn't matter. That's just because sometimes I draw a crappy arrow. But is 0 less than -4? No, 0 is never less than a negative number, so therefore it shouldn't be a part of the solution, and it's not. Number 34, s is less than 1. Numbers less than 1 include 0, right? 0, -1, -2, and those are just integer values. Even 0.5 is less than 1. Is 2 less than 1? Heck nah. Therefore, 2, which is to the right of 1, will not be included. 1 will not be included. It's an open circle. 1 is not less than itself, so we do not include 1. 0.99, sure, that's a part of it, but there we go. Number 35, 1/4 is less than p. I'm not fazed by the fraction when all I'm writing is the boundary point stuff, but 1/4 is less than p is another way of saying p is greater than 1/4. Of course, we'll be going in that fashion here. Here I have, sorry for the bad things there. 1/4 is a positive number, so it's more than 0. Barely, right? 1 is somewhere out here. 1/4, 2/4, 3/4, 4/4 is 1. But p is greater than it, not including it. So p can be 1, right? That's greater than 1/4. It can't be 0. 1/4 is less than 0 is not true. 1/4, a positive number, can never be less than 0. Number 36, the last one from this set, r is greater than or equal to the opposite of the absolute value of 5. Okay. So r is greater than or equal to the opposite of the absolute value of 5. I think it's best that we take the absolute value of 5, which is 5, but the negative still sits on the outside of that, keep in mind. So r is greater than or equal to -5. Not much to state on this one other than just draw it like that. So here we go. What's greater than that? The opposite of the absolute value of 5. Whoops. So here we're saying here's 0, here's -5. All we had to do was simplify and we go on from there. Close circle on the -5. Greater than is to the right as r compares to that number in that way. 0. Is 0 greater than or equal to the opposite of the distance from 5? Yes, it is. So there you have it. Okay, in exercises 37 to 40, write and graph an inequality for the given solution set. We're going to graph all values of x for which x is less than 7. I don't think there's a difference between what we're doing here and there. It might be that I overstuffed numbers 29 to 36 where we were supposed to test 2 points, and now here when we do the graphs, we're supposed to do the less than's left, greater than's right. That's totally okay. I'm still working on it this way. I'm graphing all values of x for which x is less than 7. Once again, there's really no difference in what we're doing here. Literally, there isn't. Here's 7. Here's 0. I'm graphing to the left of it. I'm graphing to the left of it there, like that. I think at this point, I'm not going to test points anymore, though. If the other problems were all about testing points, I think I verbally stated out loud enough points that did seem to work there. Apologies if I wasn't doing them to the letter of the textbook. But ultimately, we need to know process. Ultimately, we also need to understand what we're doing. And I hope that I'm able to satisfy both with the way that I've been going about it. But when we streamline our efforts, we are going to go greater than to the right, less than left, and the boundary points as they are. See, the book never mentioned the phrase boundary point. I'm disappointed in them. So my boundary point here is -2. My ends must be greater than or equal to -2. So we're going to go to the right of it. We're going to include it. And I always like to put the variable above. For me, it's a good way of just indicating that it's specifically for the variable. It's important when we end up solving them and that we are referring to the variable in comparison to the number. So I'm really big on it personally. I know the book's not really doing it, but they're still representing those as the solution sets regardless. All values of z for which 1.3 is less than or equal to z. Let's see if we can do this without a rewrite, but just make sense of what we have. Our boundary point is less than our number. That does mean our number is greater than our boundary point or equal to. But let's try it this way this time. Let's say our number is to the left of our boundary value. The 1.3 is to the left of all of our solutions. Therefore, this is left of the solutions. The solutions must be over here, or equal to. So, boom, and then these go to the right. So, anyway, I would want to flip it over as a whole, but I'm just stating that the less than is left can still work, just not as an arrow that time. It's just in comparison to. And then number 40, we have all the values of W for which 5.2 is greater than W, or our boundary value is to the right of all of our solutions to this inequality. If it's to the right of them, that means our arrow would go to the left, because we could also say W is less than 5.2. Here's 0, here's 5.2, and W is everything to the left of that, including 0. 5.2 is greater than 0, so that works. Am I taking the easy way out with my graphs? Absolutely. If you have your own number lines given to you by your teacher or something, great. The book didn't provide one for me. I'm going to generally do it this way for the bigger picture, which again happens to do with how 0 compares to this and where our solutions are. I'll know numbers. When I look at 5.2, I know 5.3 is on this side of it. I know 5.1 is on that side of it. I don't have to write them. The reason I put 0 is to remind us of what represents a solution to that when I test the number. And for now, I'm not fully testing the number, but there we have it. All right, on numbers 41 and 42, I'm going to leave those values where they are, the graphs where they are, and then I'm just going to go ahead and write answers. So number 41 to 44, write an inequality that represents the graph. Well, I could copy down the graph in like a quick way, actually. I could do 4's here, therefore 0's there. It has a closed circle on 4, so it's equal to 4, and it's to the left of 4 as well, so it's less than it. So, and I'm going to use x for all these. X is less than or equal to 4 is the solution to number 41. If I'm going to take the easy way out, I'm going to at least copy down the problem so I can describe what it is. Number 42, again using x in comparison to this, I have negative 2. And by the way, you can always test 0 for these still as I do this. I have negative 2 as my boundary value. Closed circle on it means it includes it. We're going to the right of it means we're greater than it. X is greater than or equal to negative 2, which includes 0, which is also greater than any negative. Numbers 43 and 44 must be on this side. Here we are. Number 43, we have on our number line, 3 is our boundary value or boundary point. Our boundary point is an open circle, and we're graphing to the right of it, so our x's are greater than that 3, not equal to it. 0 is not greater than 3, so that seems to satisfy this. 0 not greater than 3 satisfies that, and that would be our solution there. And number 44, looks like we get a taste of each type here. We have a greater than, a less than, a greater than or equal to, less than or equal to. This must be the less than. X is everything less than that negative 1. 0 ain't less than negative 1. 0 doesn't belong in the solution set. Oh, that was 44. Apologies. Okay, there are those 4. We're making good time, like I stated. Let's move on to number 45. Analyzing relationships. The water temperature of a swimming pool must be no less than 76 degrees Fahrenheit. The temperature is currently 74 degrees Fahrenheit. Which graph correctly shows how much the temperature needs to increase? Explain your reasoning. It must be no less than 76 degrees Fahrenheit. So, the difference in which our amount of water needs to increase must be more than the difference between what it must be set at versus what it's currently at. Our x's must be greater than or equal to 2 degrees Fahrenheit. So which graph represents that? It's not A, that's negative 2. So the wrong boundary values here. These are the correct boundary values, but D are numbers that are less than it. We need to be C right there. This needs to be our graph. I'm just going to kind of put C right there. They say explain your reasoning. My explanation is in right here in the subtraction. I can type it out, however. The amount we need to increase the water temperature must be greater than the difference between the, let's see, what do they call it? I guess expected water temperature. The policy, oh gosh, what's the word? Standard, whatever, the expected. I have another word. I can't think of what it is. The expected water temperature and the current water temperature. So that's my explanation. What's the word I'm thinking of? The expected, the standard, the policy. Gosh, I don't know. There's a very easy word I'm not thinking of there that's like, it needs to be this. Protocol. Number 46. According to a state law for vehicles traveling on state roads, the maximum total weight of a vehicle and its contents depends on the number of axles on the vehicle. For each type of vehicle, write and graph an inequality that represents the possible total weights, W in pounds of the vehicle and its contents. So it looks like for a 2-axle vehicle, these are maximum total weights. So maximum is the most it can be. It can be that or less. So for the first one, for a 2-axle vehicle, our weight, I'll put W for weight. Our weight cannot exceed 40,000 pounds. It can be 40,000 pounds, so it can be that or less. I think I need to put a comma there. They say graph it? They did. They said write and graph it. I'm going to do a really small graph here. So 2-axle vehicle. Here's our condition we must meet. Here's 0. Here's 40,000. Now, like I stated, eventually we're going to do what are called compound inequalities, which is a way of saying that we have to be within 2 values. Like, can we have negative weight? I don't really think so. So eventually we should really stop at 0. We're not really talking about those yet, so that's not expected that we, bring it up. So I think that's okay that we just do this for now. A 3-axle vehicle, our weight must be within 60,000 pounds. Well, within, I think, might mean you can't include 60,000. So it may not exceed 60,000 pounds, less than or equal to that. Same thing. I mean, all these graphs, guys, I'm not going to, beat around the bush with it. I'm just working this way. Less than or equal to this one, to the left there. I guess 0's included. A 0-pound vehicle. And then 4 axles, 80,000. I could have kind of just copied and pasted everything and just turned the 6 into an 8, stuff like that, because I'm not changing anything on these graphs here. A little mundane of a problem, because nothing really changes, unless, of course, I do different things on my scaling for these, but this is how they work as graphs. Okay, number 47. The Xianren Bridge is located in Guangxi Province, China. The arch is I'm looking at the picture. This arch is the world's longest natural arch. It's right here. I don't know if you guys can tell what you're looking at here. The bridge is it's kind of cool. There's the bottom of the arch. There's kind of the top of the arch. So they said it's a bridge. They say it's natural arch, so it's not man-made. With a length of 400 feet. Write and graph an inequality that represents the length L in inches. In inches of all other natural arches. So if this is the world's longest, there's nothing quite that length, so anything else is going to be less than. Not equal to, but less than. Now, 400 feet, this is a cool bridge. I want to look at pictures of it later. Hope it doesn't collapse. Hopefully someone's not on it. Hopefully there's no road on it, but hopefully someone's not on it just walking and then boom. Anyway, 400 feet. We did feet to inches before. You know what? Let's do it in the way that you would do it from previous conversion things. 12 inches for every 1 foot, like that. Feet cancel, and that's why you do 400 times 12 over 1. And that's 4,800 inches. Now, our length, L, of all other natural arches must be less than 4,800 inches, is what we're saying. And, of course, more than 0 to exist, but we're only doing that side of things. Okay. Number 48, thought-provoking. A student works no more than 25 hours each week at a part-time job. Write an inequality that represents how many hours the student can work each day. Well, you could do 20 hours in one day, 5 hours in the next day, and then no hours the rest of the day. So I think they're saying, assuming that this has on a per day basis, and it says for the week, it says each day, you could divide the 25 by 7. That's not a perfect number. I'm just going to go and work that out. If H is the number of hours each day they can work, they shouldn't work any more than 1/7 of 25, because 25 is the number total in the week. There are 7 days in a week. We divide it by 7. I'm going to write it like that, actually. 25 over 7 hours each day. I don't know what that divides into. 3.5 something, 3.6, whatever. So like 3.5 hours a day is what you should work at most if you work each day there. I don't know if that's how you'd want to say it, just because they never said that on a per day basis that they have to be equal. And listen, they don't have to be equal. But once you hit 4 hours or whatever, you've exceeded a per day basis of what you'd want to do, because then you'll start working 28 hours. So that's how I'm going to go about it. Number 49, describe a real life situation modeled by the inequality 23 plus x is less than or equal to 31. Now, keep in mind with this situation, we're not going to solve for it, so we want to do it straight up as it's written using the numbers 23 and x and such. Remember, we're not solving this kind of inequality, which is easy to do. We're not solving this kind of inequality until next section, 2.2. 23 and 31. 31 days in a month, but then that's you can't be more than 31 if that's the case for that. Let's just do money. You spent $23 on something and you only have $31, right? And you don't want to exceed it. So like you spent let's see, what do I buy? I don't buy many things. You spent $23 on electronics and you have $31 in your, and you have $31 total to spend. So like that, right? Just like that. So that's the scenario. You may not spend more than $31. So you can still spend, which is not the part we're solving, but you can still spend up to $8 more, right? $8 more. If you spend any less than $8, that still works. Sorry, you have up to $31 total to spend. If I just said total, then it sounds like an equals. Up to that amount is another way of kind of stating less than or equal to. Or at most. I can say at most $31 to spend. I got to get better at making my own inequalities like that. Number 50. How do you see it? The graph represents the known melting points of all metallic elements in degrees Celsius. Why is it negative? Why would negative degrees Celsius be melting points of all? Oh, greater than or equal to. I'm sorry. I was thinking less than or equal to. Time out. Write an inequality represented by the graph. Okay, well that one there would be x. X is greater than or equal to negative 38.87. Now, I'm still concerned about the things that melt. This is degrees Celsius, by the way. I'm still concerned about which things are negative 38 degrees Celsius and still melt in frozen conditions. That's crazy. I guess maybe they're just covering their bases. Maybe there's nothing actually that low. Part B, is it possible for a metallic element to have a melting point of negative 38.87 degrees? Explain. Now, if they asked that without context showing the number line, I would have said no. How can something that's well below freezing point still melt? I guess it's possible, but the real question is in an inequality basis. Can I substitute negative 38.37 or 0.87, for x, and is that still greater than or equal to, and I'm going to put the question mark this time, is it still greater than or equal to negative 38.87, 87, I keep saying 37. It is, it's not greater than, but it is equal to it. So yes, it's possible for this to have it because it fits within the inequality state. So this is the lowest possible melting point. This is lowest possible melting point. I still don't understand that. I need to look up pictures of that bridge. I need to look up which metallic elements have below freezing melting points. If they do. Number 51, drawing conclusions. A one-way ride on a subway costs 90 cents. A monthly pass costs $24. Write an inequality that represents how many one-way rides you can buy before it is cheaper to buy the monthly pass. Is it cheaper to pay the one-way fare for 25 rides? Explain. Okay, so anytime that you do your one-way rides, you are spending 90 cents per ride. If X was the number of rides, you're spending 90 cents per ride times the number of rides like this. This is money spent on this. This says how many one-way rides you can buy before it is cheaper to buy the monthly pass. This thing will be less than or equal to that. Sorry, spending money on monthly things This is how many rides you can do while it's still cheaper than this before this ends up being a better deal. So 90 cents per times the number of is that one. And then less than or equal to 24 is that one. So hopefully that's making sense. I'm saying it for you as much as I'm saying it for me. X is the number of times. Remember, we're not solving. We're going to test a solution on 25. But the number of monthly. Well, okay, here. Let's answer it. So here's kind of a part A. Let's do the part B. Let's do 0.90 times 25 and see if it makes sense in what we're stating. Now, I need to calculate that. Actually, I think it's 22.5. So let's see. 0.9 times 25. It's 22.5. So 22.5 is less than or equal to 24. Now remember, this is all in dollars right now. So what they're asking is it cheaper to pay the one-way fare for 25 rides? Explain. So yes, it's cheaper to, because it costs $22.50. Because 25 rides costs $22.50. Now, the first one I'm still kind of sticking with as far as the inequality. Write an inequality that represents how many one-way rides, X number of one-way rides you can buy before it is cheaper. Yes, so we have to satisfy it's still, even when it's equal to, this still satisfies it for that. 25 is a part of it. Number 52, making an argument. Ooh. The inequality X is less than or equal to 1,324 represents the weights in pounds of all mako sharks ever caught using a rod and reel. Your friend says this means no one using a rod and reel has ever caught a mako shark that weighs 1,324 pounds. Your cousin says this means someone using a rod and reel has caught a mako shark that weighs 1,324 pounds. Who is correct? Explain your reasoning. Your cousin's correct. Your friend is not. The weight in pounds of all mako sharks ever caught. Because equal to. So your cousin is correct. My cousin is correct. Custon. And my friend is not. Boom. Because reasons. The less than or equal to symbol, I'll replace that in a second, but the less than or equal to symbol means that equal to is a part of it. So 1324 is among the weights of mako sharks that have been caught using a rod and reel. So they're really just working on, listen, answering the question might be very easy, and I understand that, but this is part of reminding you and giving you a great understanding of why the or equal to part matters for these situations. 1324 can equal 1324 in these situations. Number 53, critical thinking. Describe a real-life situation that can be modeled by more than one inequality. Oh. A real-life situation. Can I convert units? Can I say like, oh, if we're dunking a basketball, our hand needs to be at least, 10 feet above the rim or 120 inches above the rim? I mean, those are the same amounts, but there's that. I got to think about this one as far as what they actually mean, and I'll come up with a good one. Okay, so I can't think of anything that's not either a compound inequality or not just a unit conversion. So, like I said, the basketball one, I think, is what I'm going to go with. I mean, you could do anything with that. We could talk about, like, grams and calories and things like that. I mean, well, like grams of fat and calories, although that would be different for each thing, and I'm not going to do research. So, like, your hand must be 10 feet above a basketball rim to dunk it. At least 10 feet, sorry. At least 10 feet above a basketball rim to dunk it. Or greater than, or no less than 120 inches. So I'm going to write two different inequalities for that. So your height, your hand, your reach is greater than or equal to 10 feet and greater than or equal to 120 inches. I don't know if even at that, I said at least. Uh, you probably have to exceed it in reality, but I'm just gonna go ahead and say that. It's whatever. Critical thinking, it made me think critically, and we'll see if I did it. All right, in 1997, Superman's cape from the 1978 movie Superman was sold at an auction. Really? The winning bid was $17,000. Write and graph an inequality that represents the amounts of all the losing bids. They have a typo here. The amounts of all the losing bids. If the winning bid was $17,000, nobody bid more than $17,000. Therefore, everything else was less than $17,000. Regarding bids, my graph is going to have 0 over here. Let's start the bidding at $0. Now, it's not equal to, the winning bid was $17,000, so here are our bids. Number 55 to 58, write an inequality that represents the missing dimension x. Here it says on number 55, I wonder if this is our introduction to solving sum. Hold on a second. The area is less than 42 square meters. Okay, I guess we're not technically solving, but we have to test values because we're not allowed to solve yet, I don't think. Now, an area of a triangle is 1/2 base times height. Now, they said the area is less than 42 square meters. So our area of this thing, 1/2 base times height, and our height is 6, is less than 42 square meters. 1/2 times 6 is 3. 3 times b, 3 times b has to be less than 42. So we have to, it says right, oh, I guess it says write an inequality. I don't think it said solve it. I'm sorry, base has to be x this time because they have an x there. So x and x like that. Are we allowed to solve? I'm going to go ahead and solve it. 3 times what number? What's the peak number here? Whatever 3 times that number is. It can't be 14. 14's that peak. So dividing by 3, you'd get 14. Ooh, I don't know how we're supposed to come up in meters. I don't know how we're supposed to come up with it without solving. We start solving using multiplication and division in section 2.3. So, I mean, listen, we can solve as much as we want, but why are they teaching it here unless they're saying plug in numbers until it doesn't work? But that's the whole point. 3 times 42, 3 times 14, I'm just going to show this. 3 times 14 is 42, so x has to be less than 14. This triangle, same thing. Area is, so 1/2 base times height. That's not a times, by the way. That's an x. Has to be less than 8 square feet. Oh, greater than or equal to 8 square feet. Greater than or equal to 8. Half of 10 is 5. 5 times your number has to be greater than or equal to 8. If you plug in numbers enough until you find out which one is the bare bottom of this number, you would divide by 5 to figure that out. And 8 divided by 5 is, well, 80 over 5 is 16. So 1.6. X is greater than or equal to 1.6 feet. That is our length for that one. So yeah, really interesting that they're solving on these ones, unless by writing we're not supposed to solve, but hey, I'm doing it. Number 57. Number 57, we have the area is less than 18 square centimeters. This is area of a trapezoid. This is 1/2. This is averaging your base and multiplying by height. So average your base, add these and take half of it, then multiply by height. We need to find height. This is area must be less than 18 square centimeters. So this area here, 1/2. Average your bases, 4 and 8, times the height needs to be less than 18. 4 plus 8 is 12. 12 divided by 2 is 6. 6 times our height must be less than 18. Whoopsie, I'm giving away answers here. 18. 6 times 3 is 18. So h couldn't be 3. It must be less than. H must be less than 3 centimeters. Oh, they used x again. X must be less than 3 centimeters. And that's what I'm saying on that one. And then number 58. The area is greater than 12 square inches. This is a rectangle. We're talking about some sort of length times width, or base times height, however you want to put it. Area has to be greater than 12 square inches. I don't know if I've been putting the other units here. This should be square centimeters, things like that. But this length times width, x times 2 must be greater than 12. So x couldn't be, 6 is the boundary value. X must be greater than 6, therefore. 6 inches. And that would be that result. So again, I don't know, like I'm doing solution stuff. I'm kind of plugging numbers in, but I'm doing division to figure it out. Is that solving? Yeah, sort of. So we're going to do those with division in section 2.3. So I guess they're having us do it a little early. I don't know if they're aware of that. They also had a typo on this other problem, so I don't know if they're aware of that either. I think it's the last question, number 59. A runner finishes a 200-meter dash in 35 seconds. Let R represent any speed in meters per second faster than the runner's speed. Write an inequality that represents R, then graph the inequality. So the running speed, it's running speed, right, in meters per second. R being greater than it, faster than it, is greater than 200 meters in 35 seconds. Now that is a fraction that can reduce. I don't know if it's a decimal that can divide, but if I divide those by 5, I get 40 over 7. So 40 meters every 7 seconds is the best I can do there. If I round that, because I want to know how many meters per second that is, 40 divided by 7 is around 5.7 meters per second. So your speed has to be faster than that. Since we're rounding, you kind of got to be careful in what you state. It says graph the inequality. So if I graph it, 40/7 or around 5.7 is obviously greater than 0. Our running speed faster than that. Woo, super fast, 20 meters per second. Things like that. Every point on the graph represents a speed faster than the runner's speed. Do you think every point could represent the speed of a runner? Explain. Heck no. Eventually, there's a certain speed that we just can't reach. No. There is a certain speed, maximum speed, that runners can reach, even though it could be more than 5.7 meters per second. I don't know what it is. I don't know how many meters per second we can cover. What are the 40-yard dash times that people can get that are the fastest? Let's say 4 was the fastest. That's 10 meters a second on average, which is super fast. Now, I don't know if that's the fastest people run, but you ain't going to run 15 meters per second or something like that. I mean, we're not cheetahs. We're not cars. We're not Teslas, things like that. So we have a limit. Even though this is it, we don't know where our threshold is. We just know that it's something faster than that is done. All right, guys. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Ooh, someone just collided. Dang, it's like hold on. I'm going to rewind that. He threw himself into the wall. Hold on. I'm going to go back to the main thing. What the heck was this? I'm going to watch this again. Dude threw himself into the wall. Okay, interesting. Anyway, this is Mr. Robinson. Thank you so much for watching. Nice streaks, man. I forgot what I was going to say. Next comes 2-2, 2-3, and 2-4. And I keep bringing those up because those are all solving inequalities, but they go slowly through them in learning how, remember how we solved equations before, addition, subtraction, multiplication, division. We're going to eventually get to that kind of in section 2-4. I believe we're going to get to the level of parentheses and distribution and all that to finally solve them. So thank you guys so much. Take care. I'll see you in those next ones.